Hello everyone, myself Preeti Kiran, PGT Chemistry from Kendriya Vidyalaya number 1 Air Force Station, Hindon. Dear students, I am taking the solid state. It is the first unit of class 12th chemistry and it is the part 3 of the video session. Dear students, I have told you that on the basis of the arrangement of the particles, the constituent particles, the solids are classified as the crystalline solids and the amorphous solids. We talked about the perfect orderness and the arrangement of the constituent particles, and we defined the crystalline solids as: in a crystalline solid there is a regular arrangement of the constituent particles. They have long range order in the arrangement of their constituent particles. The constituent particles can be atoms, molecules or ions. But is there a perfect crystal? Let's see. The perfectness, the orderness is not found to be perfect. In nature, the crystals are not found to be perfect. And if they are not perfect, then how there is the imperfection, and what is the reason behind these imperfections? What are the types of imperfections? Today I will explain that. Today's topic is imperfections in the solids, or we can say that the defects in the solids. Any departure from the perfectly ordered arrangement of the constituent particles in the crystal is called imperfection or the defect. On the screen you can see a picture in which there are various reasons depicted due to which there is a defect or the imperfection in the crystal. The picture shows you the mixture of the reasons for the defects. We'll take up these one by one. Why do imperfections or the defects occur? Imperfections or the defects occur due to fast or the moderate rate of crystallization, because the constituent particles, they do not get the sufficient time to arrange themselves in the perfect order. During the preparation of even single crystal, by carrying out the crystallization at extremely slow rate, these single crystals may not have the perfect arrangement. The types of the defects. There are two types of defects, the point defects and the line defects. The point defects. When the deviations or the irregularities exist from the ideal arrangement around a point or an atom in a crystalline substance, the defects are called the point defects. Now just look at this picture. It has variety of the point defects. No doubt we will take them later in detail, but just have a quick look. It is a vacancy defect just at a point. Here there is supposed to be an atom or a constituent particle, but it is missing. And in this, it is self-interstitial, means in addition to the normal positions, there is one extra constituent particle placed in the interstitial space or the interstitial site. Here there is this is the internal reasons, the intrinsic point defects. Now the extrinsic point defects. This is some foreign body, the substitutional foreign atom in the crystal. Here the interstitial foreign atom, it has replaced the original site, and here in addition to the normal positions, there is some foreign impurity in the interstitial site. The line defect. When the deviation from the ideal arrangement exists in the entire row of the lattice points, the defect is called the line defect. Here the defect is along the complete line. It is not only situated at a point. So this is the line defect. the types of the point defects. We will study in detail about the point defects. The point defects are of three types: the stoichiometric defects, the impurity defects, and the non-stoichiometric defects. The stoichiometric defects. Now first of all we have to understand what do you mean by the stoichiometry. If the defect in the crystals are such that the ratio between the cations and the anions remains the same as represented by the molecular formula, that is, the stoichiometry of the solid is not disturbed, the defects are called the stoichiometric defect. These are also called intrinsic defects, that is, the deviation within the crystal, or thermodynamic defect due to the absorption of heat from the surrounding. So up till this, the stoichiometric defects are those defects that even after the defect, if the stoichiometry of the solid is not disturbed, then the defect is known as the stoichiometric defects. Now the classification of the stoichiometric defects. In the non-ionic solids, it is vacancy defect or interstitial defect. But in the case of the ionic solids, it is Frenkel defect or the Schottky's defect. Now let's take the stoichiometric defects in the non-ionic solids. The first is the vacancy defect. Let's study it in detail and understand what is it and what is its impact on the properties of a solid. When in the crystalline substance, some of the lattice sites are vacant, the crystal is said to have the vacancy defect. Now see this picture. Here it is supposed to have a constituent particle, but it is missing. There is a vacancy created here. So the name given, the vacancy defect. This generally arises due to the absorption of heat from the surroundings. That is why it is known as the thermodynamic defect. It results in the decrease in the density of the substance. Now why decrease in the density of substance? Because the volume is same, but there is a decrease in the mass, because from this site the constituent particle is missing. So there is a decrease in the mass, but the volume is same, and you know that density is equals to mass upon volume. So due to the presence of this defect, the vacancy defect, there is a decrease in the density. I have earlier told you this defect is shown by the non-ionic solids. Now the interstitial defect. Interstitial defect is again shown by the non-ionic solid. Now just see the picture. These are the assigned positions, but you can see this constituent particle and this one. These were actually the interstitial sites, but accidentally the constituent particles, they occupy this position also. No doubt they are at their assigned positions, but in addition to that they are present here also in the interstitial positions. Now let's read what is given. When some constituent particles are present in the interstitial sites, the crystals are said to have the interstitial defect. And I know you must have understood that now there will be an increase in the density of the substance. It is just because the volume is same, but the mass is increased. So due to the interstitial defect, there is an increase in the density of the substance. Dear children, we do ask you this question, that there is a defect in the non-ionic solid and there is an increase in the density. So what type of defect is there? So you have to answer that it has the interstitial defect. And if the question is opposite to this, that there is a decrease in the density, then your answer will be that there is a vacancy defect. Now, the stoichiometric defects in the ionic solids. They are named as the Frenkel defect and the Schottky's defect. Now we have to study these two in detail. Here we have two pictures. This one is for the Frenkel defect and this is for the Schottky's defect. Now let me explain these two together and then we will take up one by one in detail. Now just focus your attention on this figure. Here this is the position which was for the cation. Here when we see all this alternate arrangement, then we can very well know that this is the position which was assigned to a cation. But in this position the cation is missing. Here you can see a vacancy. Now where this cation has gone? Just look here. It is here in the interstitial site. Now dear children, just understand this. This is the cation. It is present in the crystal, but it has left, it is misplaced from its original site and it has entered into the interstitial space. So it is a mixture of two defects. Here it is a vacancy defect and here it is the interstitial defect. And now I think that you can very well imagine that what will be its impact on the density. That we will study later on. Now just focus your attention on this figure. Just see these two positions. Now here it was the position for the cation, the yellow one, and this is the position assigned to the anion, the blue one. Now both are missing. Cation from this situation, the yellow one is from this situation and the blue one, the anion from this situation, both are missing. Just check. They are not present in the interstitial site. They are missing. They are missing. They have left the crystal and both of them have left in equal number. And the stoichiometry of the crystal is not disturbed. When the cation and anions are missing, that is a Schottky defect. And when the cation, which is usually smaller, occupies the interstitial site, it is misplaced. Here will we use the term misplaced, here missing. So let's take up each defect one by one. The Frenkel defect. In this defect, an ion, smaller ion, usually cation, is missing from its lattice site, causing a vacancy or a hole there, and occupies the interstitial site. In this defect, the electrical neutrality as well as the stoichiometry of the compound is maintained. This defect is a combination of vacancy defect and the interstitial defect. It is also called the dislocation defect because smaller ion, the cation, is dislocated from its normal site to an interstitial site. The density of the solid remains same since no ions are missing from the crystal. I hope up till this the concepts are clear. Types of the compounds exhibiting the Frenkel defect. The Frenkel defect is shown by the compound which have the low coordination number and the large difference in the size of the cations and the anions. Cations small and the anions large. So you can see in the figure, cation from its original site has been dislocated and it has entered into the interstitial site. The Frenkel defects are found in, the common examples are silver halides, silver chloride, silver bromide and silver iodide. It is just due to the small size of silver ion. Zinc sulfide also shows this Frenkel defect. It is just because of the small size of the zinc ions. They are not found in the alkali metal halides as the alkali metal ions cannot fit into the interstitial sites because of their large size. It's a frequently asked question that which type of defect is present in the silver halides or the zinc sulfide, and they ask the reason also. So whenever it is a question regarding the silver halides and the zinc sulfide, you can write that the Frenkel defect is present, and the reason is the cations are smaller in size and they can very well occupy the interstitial sites. And this defect is not shown by the alkali metal halides because the alkali metals like sodium, potassium, etc., they have the large sized cations. Now the another defect in the ionic solids is the Schottky's defect. If in an ionic crystal of the type XY, equal number of the cations and anions are missing from their lattice sites, so that the electrical neutrality is maintained, and it is called the Schottky's defect. It is basically a vacancy defect. As the number of the ions decreases, the mass decreases and the volume remains the same. Hence, density of the solid decreases. Now, I am taking this picture on the next slide so that you can see the defect very clearly. Now, dear children, you can see this position. This is the position for a cation and this is also for a cation. And these are the positions for the anion. Now, in the figure you can see the two cations and the two anions are missing. They have not occupied anywhere the interstitial site. So when the cations and the anions in the equal number are missing from the crystal, then it gives rise to a Schottky's defect. And since the ions are missing, there is a decrease in the mass, but the volume is same, so there is a decrease in the density. And you can say it's basically the vacancy defect. So when in the ionic solids we usually give a question that there is a decrease in the density, what type of defect it is. So you have to write the Schottky's defect. Now let's study what type of the compounds exhibit the Schottky's defect. The compounds which have high coordination number and there is a small difference in the size of the cations and anions. You have to remember all these points because in the exams we also give you a question that what is the difference between the Frenkel defect and the Schottky's defect. Schottky defects are found in the ionic compounds NaCl. This is an alkali metal halide. Sodium chloride, potassium chloride, potassium bromide. And just see, here AgBr is also written. AgBr was also mentioned in the Frenkel defect. So now please remember this, that AgBr shows both the Frenkel defect and the Schottky's defect. Actually, the size of the silver ion is like it can occupy the interstitial site also. So it shows the Frenkel defect and it shows the Schottky's defect. And dear children, it is the frequently asked question that give an example which shows the Schottky's defect as well as the Frenkel defect. So your answer will be AgBr. This is the tabular form, the difference between the Schottky's and the Frenkel defect. Do make your notes and write these points of differences in your notebook and remember that. Now dear children, there is another picture on the screen and you can see it is actually a crystal of sodium chloride. Just see the sodium ions and the chloride ions. And now see very attentively, you can see strontium Sr2+. Now in the crystal of the sodium chloride, there is some foreign body, there is a foreign ion and hence it is an impurity. And just see here, there is a vacancy. This position is of the sodium ion and the sodium ion is missing. Now why sodium ion is missing? What type of defect it is? Now let's study what type of defect it is now. This is the impurity defect. These defects arise when the foreign atoms are present at the lattice site in the place of the host atoms, and such are known as the substitutional solid solutions. Or at the vacant interstitial sites, then they are known as the interstitial solid solutions. Introducing the impurity defect in the ionic solids. Now let's understand the details of this. In the case of the ionic solids, the impurities are introduced by adding the impurity of the ions. If the impurity ions are in a different valence state from that of the host ions, the vacancies are created. Now let's understand what does this mean. Just I shown you a picture in which the strontium ion has occupied one side of the sodium ion. Now you know that sodium has +1 charge, but the strontium has the +2 charge. So strontium has occupied the sodium ion site, but it has also produced a cation vacancy. It is just because it has the 2+ charge. So 2 Na ions will have to be removed. Why? Just to maintain the electrical neutrality. One of these sites is occupied by the strontium ion and the other remains the vacant. So just to maintain the stoichiometry, just to maintain the electrical neutrality, the cationic vacancy is generated. Now let's focus on the non-stoichiometric defects. The defects or the imperfections in the crystal due to which there is a difference in the ratio of the cations to the anions from that of the indicated by the ideal chemical formula. That is, the stoichiometry is now disturbed. Then such defects are called the stoichiometric defects. Such defects are called the non-stoichiometric defects. Now let's classify. The non-stoichiometric defects are classified, or the types are the metal excess. Now the metal excess is why? Due to the presence of the anion vacancy, or the metal excess may be due to the presence of the extra cations. And then the metal deficiencies. The metal deficiency due to cation vacancy, or the metal deficiency due to anion excess. Now let me take up each one by one. Metal excess defects. The metal excess can be there due to two reasons. One is by the presence of the anion vacancy, and the other one is by the presence of the extra cation occupying an interstitial site. The metal excess defect, the first case, by the anion vacancy. A negative ion may be missing from its lattice site, leaving a hole which is occupied by an electron, thereby maintaining the electrical balance. The site containing the electrons thus trapped in the anion vacancies are called F centers. It is a German word for color, Farbencenter. They are responsible for imparting the color to the crystal. Now let me explain this. Now actually what happens? Suppose this is a crystalline solid. Now this is the position which was assigned to an anion. Now anion is missing. And what is there now? The anion vacancy. Now this anion vacancy is occupied by an electron. And when an anion vacancy is occupied by an electron, when an electron is trapped into this, then this point is known as F center or the Farbencenter. It is a German word. And this point, this F center, is responsible for imparting the color to the crystal. More the F centers are, stronger is or deeper is the color. I am taking an example from the text only, from the NCERT, to explain this F center. On heating NaCl, a sodium chloride crystal, in an atmosphere of the sodium vapors, the excess of the sodium atom, it deposits on the surface of the sodium chloride crystal. Now what happens next? The chloride ions which are present inside the crystal, they diffuse to the surface where they combine with the sodium atoms which become ionized by losing electrons. Now what happens? The chloride ions, they have diffused on the surface, and the sodium atom, they change into sodium ion by losing the electron. And now this electron, it diffuses into the crystal and it occupies the vacant side created by the chloride ion. And this is the F center. These electrons, they absorb energy of the visible light falling on the crystal and get excited, giving yellow color to the crystal. We were taking the example of NaCl, so the color of the NaCl comes out to be yellow. This is the common question which is asked in the exam. Why common salt is yellow in color? And you have to write it is due to the presence of the F centers. And due to the same reasons, the lithium chloride crystals are pink in color and the potassium chloride crystals are violet in color. Now the metal excess defect due to the presence of the extra cation at interstitial site. Again I am repeating, the metal excess defect due to the presence of extra cation, metal excess, extra cation at the interstitial site. Just look at the picture. They are all at their assigned positions, but there are extra cations in the interstitial site. The electrical neutrality is maintained by an electron present in the another interstitial site. So here is the cation and just in the neighboring interstitial site we have this electron present. So the electrical neutrality is maintained. Now let's understand this by taking a suitable example. When the zinc oxide, which is white at the room temperature, when heated, it loses oxygen and it turns yellow. Zinc oxide, which is actually white in color at the room temperature, it loses oxygen and it turns yellow. Why it happens? Let's study from this equation. Actually, this is white in color, zinc oxide. We started heating it. On heating, what happens? Oxygen is lost. And these are the zinc ions and the electrons lost by this zinc ion, zinc. These excess of the zinc ions, they are formed and they get trapped into the vacant interstitial site, and in the neighboring site these electrons are trapped. The free electrons, they get trapped in the other interstitial site. This is again a frequently asked question. We give this question that why zinc oxide turns yellow on heating. Now the metal deficiency defect. This defect occurs in those solids which are difficult to prepare in their stoichiometric composition, and they contain less amount of the metals compared to the stoichiometric composition. This occurs in the metals which show variable valency, that is the transition metals. Transition metals show variable valency. As you know the example of the copper, Cu plus and Cu2 plus, the cuprous and the cupric. And same way you know about the iron also, Fe2 plus, that is ferrous, and Fe3 plus ferric. Such type of the metals which show variable valency, they show this defect, the metal deficiency defect. With an example, it will be very nicely clear to you. This defect generally occurs due to the missing of the cation from its lattice site. The cation is missing from its lattice site, and the presence of the cation having higher charge. Example, +2 instead of +1 in the adjacent site. So they contain the less cations in the proportion. Charge is equalized, but the cations are lesser. I am taking this picture to the next slide to explain you again that actually what happens. Now just see, this is a FeO crystal. Now what happens actually? The Fe crystal, Fe ions, Fe2 plus, Fe2 plus ions, that means the ferrous ions are missing, and that position is occupied by the ferric ions, Fe3 plus ions, and thus the cations, the number of the cations is less, but the charge is balanced. So today we studied about the defects, the line defects and the point defect. Then we studied about the classification of the point defects, that they may be the stoichiometric, non-stoichiometric or the impurity defect. Then we studied in detail about the stoichiometric defect, that the stoichiometric defects are present in the ionic solids and the non-ionic solids. In the ionic solids or in the ionic compounds, they are named as the vacancy defect and the interstitial defects. But in the ionic solid, they are known as the Frenkel defect and the Schottky's defect. Then we talked about the impurity defect and then the non-stoichiometric defect due to the metal excess or the metal deficiency. I hope it's very much clear to you. Now let's do quickly few questions. Now let me check what have you learned so far. The first question is, in which of the following defects the equal number of anions and the cations are missing from the lattice site? Cations and anions missing from the lattice site. The options are vacancy defect, interstitial defect, Schottky's defect and the Frenkel defect. The answer is Schottky's defect. Dear children, here you have to keep in mind, you must be few of you must be thinking that it is a vacancy defect. But let me tell you why it is an incorrect answer. Because the term vacancy defect and the interstitial defect was given for the non-ionic solids. But they have mentioned here the anions and the cations. That means they are indirectly indicating you that it is an ionic solid. So you cannot use these two terms here. And when they are talking about the missing, then it is a Schottky's defect. I hope I am clear to you here. Now the next question is, which of the following defects is not a stoichiometric defect? So we know that these are all stoichiometric defects. So, and this is the non-stoichiometric defect. Let's see whether we are correct or not. Metal excess defect. Which of the following defects does not cause any change in the density of the crystal? Does not cause any change in the density. Frenkel defect, interstitial defect, Schottky defect and the vacancy defect. So the answer will be the Frenkel defect. Now let me explain you why. You know about the vacancy defect, there is a decrease in the density. Schottky's defect, again there is a decrease in the density because cations and anions are missing. In the interstitial defect, I have told you that in the non-ionic solid, some extra molecules or the constituent particle, in addition to their original positions, they also occupy the interstitial sites. So there is an increase in the density. So there is only Frenkel defect, which of the following defects does not cause any change. In the Frenkel defect, there is no change. In AGBR, there can occur only Schottky's, only Frenkel, both A and B and none of these. I hope answer is very clear to you, and it is both A and B. That means C option is correct. Now this is a figurative question and it is also asked in the exams. They give you a picture and from the picture, by observing the picture, you have to answer. So first of all, you just see this picture and let's see what is the question. Examine the illustration of the portion of the defective crystal given below and answer the following question. What are these types of vacancy defects called? Now you can see that minus plus is given, so it is an ionic solid. Now just see here, here the cation is missing. Here everything is there. Here an anion is missing. And then just look here again and you will see again there is an anion missing and here a cation missing. So the cations and anions in equal number are missing and nothing is there in the interstitial sites. So I hope your answer will be clear to you in your mind that it is a Schottky's defect. Now the part B on the same figure, how is the defect of the crystal affected by these defects? Now since the ions are missing, so the volume is same, the mass is less, so the density will decrease. Name one ionic compound which can show this type of defect in the crystalline state. So the answer is a sodium chloride crystal. Here you can write AgBr also because you know that AgBr shows both the defects. How is the stoichiometry of the compound is affected? Now there will be no effect on the stoichiometry because the cations and anions in equal number are missing. Thank you so much. I hope the lecture is very much clear to you. Just go through your NCERT, understand the concepts, practice as much as questions you can. And you must have realized that the perfect crystal is the talk of the idealization. There is nothing perfect crystals in the nature. Thank you so much.